Hi everyone, today I want to share something of using sketching technology to optimize our services with few resources. A little bit about myself. I'm Yichen. I've been working on HPC and high available distributed system for more than 15 years. And I'm a fan of functional programming as well as category theory, type theory, domain theory. That's probably because like my major are math and computer science. And I'm also a fan of the serverless and Lambda, like the technology of WebAssembly, WASI, and etc. Today, I'd like to talk about the trade-offs between performance and cost since it's P99. First, I'd like to introduce some challenges and assumptions in a distributed storage system. First challenge is the data size. Nowadays, the data size is getting larger and larger in our systems. And the second one is that data is stored in different places. In the architecture like data lake and the increasing usage of the large language model, data could be in any format, anywhere. Heterogeneous architecture is getting popular in nowadays, and it brings us a new challenge to store our data. And also, based on this assumption, there's a side effect of unbalanced data. Yeah, because data stored in anywhere, which means that the data size is different as well in different storage and different format. Okay, so based on the assumption above, what's the ideal goal to do the optimization in a distributed storage? The first goal is that we want to reduce the data size without information lost, so that we may want to use some new data structure or the compression algorithm to reduce the data size. Second is that data locality matters. We want to reduce the communication between different nodes, even different regions, so that we can increase the locality for the data. And also, it can be totally avoid for the data communication. So the third one is that we want to increase the throughput based on some hardware and software technology like RDMA, DPDK, or IO-Uring, etc. There are many papers to address this one. For example, the line is to minimizing the distributed transaction through adaptive replica provision, which to do the trade-off between the node levels transferring as well as the data locality. Okay, what's the reason behind our goals? So this diagram is something I like to share every time when I'm talking about the optimization. Of course, there's another diagram for GPU when I talked about the machine learning part, but the idea behind is very similar. We want to make CPU or GPU busy, yeah, which means that we want to push the data too close by the CPU or GPU. But in reality, of course, there are a lot of trade-offs. For example, we have a cap, we have a RAM, there are popular trade-offs in the industry in distributed system. But for us, for the scalability, I think the trade-off is that it's really hard to do the scale linearly, and also we cannot scale infinitely, because no matter the cost or the physical loss. And besides tech part trade-offs, we also have other trade-offs. As here, we have many other trade-offs. Here, I want to highlight the trade-off between the cloud and the on-prem solution. There's always a debate of the cost between cloud and self-hosted services. What does cloud bring to us? And what's the cost? If we consider the infrastructure cost only, for most of the use cases I saw, cloud will increase the cost during the building of our services. But on the other hand, cloud will give us the flexibility and also the less cost when we do the maintenance work. So there are many trade-offs and the debate for the cloud versus the self-host. Yeah, here are some papers like for the scalability versus the cost, and also I would say there are so many blogs that like this, for the migration from the cloud to self-hosting or vice versa. Okay, so let's go back to our topic. We already have the challenge of the distributed storage. Then what's next? What should we do to improve the performance as well as reduce cost? For us, we are using sketching to do the optimization for the performance. Also, based on the sketching, we can reduce our cost. There are 3 case studies I want to share today, and I promise there won't be any math formula or complex calculation. I'll try to explain it based on our user cases intuitively. First case is the usage of the DynamoDB. We use DynamoDB a lot in our systems. Something always worries us is that the hard limit of the DynamoDB RCU and the WCU for the hot partition. And also, when we have the large traffic to hit the DynamoDB, the cost of the RCU and the WCU also a concern for us, because we need to pay more for the DynamoDB usage. And here's our user case. First, we have a large volume of traffic to hit the DynamoDB, for the read and the write. And the second is that our data size is really huge. And the last is that in our business logic, we have a lot of data miss based on the logic. Then all these 3 items sum up. It will cost a lot for DynamoDB solution. Then based on the challenge, Bloom filter just in our radar, because we have a lot of data miss, so we think a Bloom filter, we could use a Bloom filter to benefit our user cases with less hit of the DynamoDB, first to improve our performance, and second to reduce our cost. So here's our new solution, with Bloom filter. First, our service will hit the Redis based on Bloom filter algorithm with different hash function, in the binary format, which it's simple to implement of a Bloom filter. And if there's a negative result from Bloom filter in Redis, then we just return to the client directly. And otherwise, we will double check in the DynamoDB to see if the data existed or not. So based on this architecture, first, because Redis is faster than DynamoDB, and then our performance is getting better. And the second is that because there are many data miss in our user cases, so we reduced a lot of traffic from our service to DynamoDB, which saved us a lot in this architecture. The second case is to calculate the cardinality in our dataset. So the requirement is that we want to calculate the device Unicode device number from some result of the knowledge graph. and we have different clusters based on the knowledge graph. And the data in each cluster is unbalanced. So also, we just do it for some analytics. So we don't need a very accurate data. On the other hand, we want to limit our cost as well as to improve our performance for this kind of analytics. So based on our the data structure, we have this multi-tier calculation data structure. For some small cluster, we are using set as it very simple to do. And for some medium cluster, we are using bucket-based method to store and calculate the result. And the best interesting part is that for the large-sized cluster, we are using some sketching-based method to do the cardinality calculation, which we are using hyperlog to do the calculation. The structure behind hyperlog is very interesting. First, it will hash the data based on some uniform distribution, and based on the binary formatted hash data, and we will use hyperlog to with some harmony means to calculate the possibility of the cardinality in our data size. So why it's called hyperlog? Because the space usage could be the log cost based on this algorithm. Meanwhile, we can have a relatively accurate solution result based on this hyperlog architecture. Yeah. But there are also challenges when we use hyperlog. The first one is that we need to hash each item to a uniform distribution, which is not easy, because there are many hash functions, and also our data based on our data characteristics. So it's really hard to pick a hash function to hash it to a uniform distribution. And also because there are many hard and computation, the distribution of the data is hard to predict, which means that we cannot do some optimization based on the CPU cache line, and which could impact our calculation performance. Then, based with all the challenges, then CVM is under our radar. Yeah, CVM is another algorithm that to do the cardinality calculation, and it's based on the pure probability methods. The solution is really simple and beautiful. I will share in the next slides. And also, the benefit for the CVM is that first, it doesn't need to hash the item into the uniform distribution, which means that the hash function won't vary anymore. And the second thing is that because we don't need to hash, which means that we can control the format of each key. And then we can do some better compression or CPU cache line optimization for this one. Yeah, here is a simple algorithm of the CVM. As you can see, it's really simple. It's just based on some probability method with limited data size, similar to hyperlog. But on the other hand, we can do many detailed optimization based on this method. And with this, we can first reduce the cost of the space usage, and also the performance is so good because the calculation is simple than other solution. Okay, the last case I want to share is how to do the hash with the similarity. So here's the requirement. We want to calculate the the distance between two IPs. But the challenge is that all the IP are hashed. So the reason behind that is that first, the IP is PII based. We don't want to share the IP location everywhere. And the second is that we want to find a simple solution like to do this kind of calculation because the data size is so huge. I think the simple solution is that we have some hash method like the geohash or cold tree hash. Like for geohash, it's really simple, but with a trade-off of the, the space usage as well as some, the nearby point between different hash. And cold tree, I think on the other side, like can give like a more efficient space storage. But on the other hand, it will have some performance penalty when there is a node split. So no matter we use geohash or cold tree hash, like I think we cannot avoid the PII like complaints because there are still concern from the PII complaint team that like we could tell some information based on no matter geohash or cold tree hash. So then next, like we think, how about we just use some similar way, like in the large language model or the vector database? Can we use locality sensitive hashing method like to do it instead of like to calculate the distance, which like is a concern from the PII? Can we just like to do the projection from the high dimension to the low dimension and to calculate the similarity? So we don't need to like to the distance anymore. We just calculate the similarity of these two data point, and then to see like if there's any correlation or collection like connection of the different hashed IPs. That's the idea like behind we want to use a locality sensitive hashing. The idea behind the locality sensitive hashing is really simple. Like we will map all the data into different buckets from the high dimensions to the low dimensions. And then in each bucket, we have some rules like to define the similarity, which here is very interesting because like the distance is only one characteristic like for the criteria of similarity. We can add other criteria for the similarity for free. So with that, first it can address the PII sensitive concern, and on the other hand, like we can add more features and attributes or labels like to this kind of like methods, like in the future, like for not only for engineering but also for machine learning. Like for example, we can combine the distance with other correlation like to this locality sensitive hashing algorithm like to do the further investigation. Though there are always a trade-off, yeah, because like if you search for some trade-off of the locality sensitive hashing, there is a paper like I said that locality sensitive hashing does not guarantee privacy. So that's also another concern, even though it's only in academic, but there's still a concern for us. So based on this paper, what we want to do next is that we may want to use some differential privacy method combined with locality sensitive hashing, like to first to guarantee there's no privacy concern, and also we want to calculate the similarity like for different hashed IPs. Okay, so that's the last case. And takeaways. First, design a scalable distributed system is really hard, no matter for storage or computing. And second, we need to know our requirements first. As well, we need to know our trade-offs as well. And then, based on the requirements and the trade-offs, let's embrace embrace some sketching and math methods so that we can improve our performance as well as reducing the cost in the system. Yeah, that's all for today. And thank you very much for your time and enjoy the P99. Thank you.